assign the homework for you to do it, to make sure that you watch the lecture. You feel free to come up with questions even if you did not watch the lecture, that's fine. So let's start. So in that lecture, this is, here we are with the introduction to differential geometry. So in this lecture, I would call it last lecture, because we did not have it in class, but we had it online, okay? We had something like why differential geometry, in mechanics at least, and how, at least in mechanics, and how the configuration space in many mechanical systems, they are curved spaces, so we need a mathematical tool to do calculus on curved spaces, and this is precisely differential geometry. So this topic was covered in that lecture. Also, the basics, the very early basics of differential geometry, like manifold, the concept of a manifold, and tangent space, have been covered very briefly, because this wasn't in dynamics. This course is mainly focused about this, so actually today is to talk formally, very formally, about these guys. Just over there we had a glimpse on what is a manifold and tangent space. So actually this lecture is just, the formalities, very formal definition of actually manifold. We will not even have time to talk about tangent space. This is tangent space here. Okay. So I will just refresh your memory about what is a function. F is a map, right? Between two sets, two spaces, two entities. So, like this is x, this is y, and we have a map that maps every point in x to some point in y. Okay? Maybe. So, by definition, if f is defined on all of x, it has to be defined on all elements of x. Okay? So, you have to give me like arrows going from every point here to some point there. Every point, maybe this guy maps to the same point, that's fine. Okay? I mean, if you took the dynamics with me, you remember the example of fruits and days, right? Yeah, I won't go through it again. Like I said, it has to be defined on all elements of x by definition for function. But for a function to be well defined, I can't. So, for example, that's okay if I have 2 points like these mapped to one point. You all guys know the very famous function f x equals x squared. So it maps -1 and +1 to the same point, which is 1, right? This is x and this is f, right? That's okay. So 2 points can go to 1 point, that's fine, but not the other way around, in the sense that if you have this guy maps to that guy, it cannot map again to other point. This is not well defined. So in math, when I ask you, I'll not ask you, but if you want to prove that a function is well defined, then you want to show that given the same input, it cannot map to different choices, and so what I'm trying to say is that this picture should not exist. So this function, say, I cannot say that this is a function, so because there are two possibilities for the point 1 to be mapped up or down. So this is not a function, this is not well defined, okay? I might not be able to cover all the points here. There might be some points left, that's fine. Okay? And here I will talk about what are some types of these maps or these functions These are the most common ones, like injective. These are just basics because we're going to speak this language a lot. Injective means like one-to-one. The name is very expressive. So every point maps to exactly 1 point. So I will not see this picture again. The 2 points map to the same point. So the function f of x equal x squared here is not one-to-one, obviously. Okay. Then we have surjective, which is, we give it the name onto, meaning I will reach all the points here. So for any little y element in y, there exists some x such that y is equal f of that x. Okay? So I can reach all these points. Obviously, again, the function f of x equal x squared is not surjective. Why? Because I cannot reach any negative value. Okay? But the function.
So does that mean the range of y is all the real numbers, right?
For a function from real to be surjective, yes, the range has to be like this example, f of x equal x cubed, right? This is one-to-one and onto, right? So, and if you combine both, you get the bijection. So bijective means one-to-one and onto. So every point maps to just only 1 point uniquely, and you cover the entire range of y. So obviously in this case you can define an inverse to be the pre-image of your point, right? That's fine, because you can reach all these guys. So now I can define a function on y, right? On all points of y to be the pre-image, that's fine. So I have a bijection, I can define an inverse fine. If I have, I don't want to go into subtle things anyway, but if you have a bijection, certainly you can define an inverse, right? So, any question about that? And you can keep adding more properties, but I'll jump to the property that we want. Diffeomorphism, CR diffeomorphism. So CR, I mean, you remember last lecture before was C0 means continuous, right? And C1 means differentiable, continuously differentiable. C2 twice differentiable, up to C infinity, infinitely differentiable, and we have the other analytic, right? So CR, you can put anything, maybe continuous or C1 just differentiable or C infinity. Typically we'll talk about C infinity here in this course. So infinitely differentiable. Diffeomorphism, okay, what is a diffeomorphism? So first of all, it has to be CR differentiable, so it's a smooth function. I will use CR differentiable and smooth interchangeably in this course. Okay? So it's a smooth function, it's also bijection. So it's one-to-one and onto, every point maps to uniquely to a single point. And it's smooth with smooth, again, so it's CR differentiable. Smooth. Smooth inverse. Okay? So yes, bijection is sufficient to have an inverse. Yes, you have an inverse, but not necessarily smooth. Okay? So going forward smoothly, going backward smooth. So if you look at this definition, if two sets, x and y, are diffeomorphic, means what? There is a map between them, and the map is diffeomorphism. What does it mean? The map is one-to-one and onto. So for every element here, there exists a unique element there. So I can go forward and backward uniquely. Going forward is smooth, going backward is smooth. So the two sets are almost identical. Right? You can go from any point here to any point there uniquely, go forward and backward in a smooth way. So mathematicians, when they want to prove that there are two sets that they look like each other, they are almost identical, they prove that they are diffeomorphic. There is a map between them and you can differentiate it almost many times. The map has an inverse and the inverse also is smooth. Okay? Some people might confuse this with the inverse function theorem, so I'll leave this to you as a, as a take-home task. Because some people think that being smooth and bijection, this already automatically takes care of the smooth of the inverse. This is not true in general. You need to add more properties. So I'll give you this example first. Example. Sometimes it will be very rigorous, sometimes it will be a little bit sloppy in this course, depending on what you want to do. So here is a map. Take this map. F maps from 0 to 2 pi is open, to S1, the unit circle, defined by e to the it. So it's cosine t and sine t in the complex or two-dimensional plane, doesn't matter much. So for example, here is 0, here is 2 pi, this is the real line, okay? And here is your circle, S1. So this point maps to that point, okay? And this guy maps here, this guy maps here, and so on. So the point pi maps over there, and then this guy maps here, and so on. So until this open point, and this is the corresponding open point. Okay. So F is smooth, you can differentiate it many times as you like, and it's actually bijection, right? Because every point maps exactly to one point. There was a possibility that these 2 points map to the same point, but this is why we excluded it, right? So F is bijections, 1 to 1 and 1 to everything is okay. F is smooth. Bijection is implies that there is an inverse, right? Yeah, I can define the inverse of any point here to be the pre-image. That's fine. But let's look. So the inverse exists because it's a bijection already. But is it smooth? Well, I'll give you the contradiction. F is not even continuous. Why? Because F inverse of this point, 1 and 0, that point, is what? What is the pre-image of 1 and 0? 0. Very good. And this is also equal the limit from above. So if you're coming to this point from here, it's as if you're coming from this point to here, right? So this is the limit F inverse of x as x goes to 1, 0 from above, right? So if I'm going here in this direction, yes, I'll converge to 0. But if I'm going to this point from below, if I'm going in this direction, so now I'm going in that direction. So if I'm going from below, this is not equal to the limit from below F inverse of x. X goes to 1, 0 from below, because actually this limit is equal to what? 2 pi, right? So the limit from the left is not equal to the limit from the right. The function is not continuous at the point. Okay? So here is an example for C infinity smooth function, bijective, but the inverse is not continuous. If you added more properties like this, if it's closed, and if you have C infinity bijection, or at least continuity, you ensure continuity. So I'll give you this as an exercise. Check how this is not in contradiction with the inverse function theorem. Okay, it's not a topic in this course, but just for the sake of your math training.
So Professor,
This is one aside, not yet.
so this function does not have an inverse?
It does have an inverse, but the inverse is not continuous. It does have an inverse. Give me a point, I'll give you I'll give you the value of the inverse function. So if you give me this point, here's the value of the inverse function. It exists,
Okay.
but it's not continuous. Because why I'm stressing this? Because I'm telling you that these are different requirements. The diffeomorphism is a map that is smooth, it's invertible, right? And the inverse is not anything, the inverse has to be smooth. So this is an additional requirement. Because the inverse function theorem says if it's one-to-one, I mean if it's from R to R, for example, if it's a differentiable function and it has a non-zero derivative at a point, then the inverse exists, of course, and it's smooth already, you get it as a byproduct. So this is not the case here, I mean there's a slight difference. So this is an additional requirement, the inverse has to be smooth, okay?
So this function is not diffeomorphism.
No, this function is not diffeomorphism. Yeah, that's good. Okay? So now we are in a point to define a manifold. So a manifold. And this is what we did in the online lecture. And by the way, we will do this like a few times throughout the course. When I assign a lecture, I mean, I really mean it. I mean, it's as if we should have it here, but we don't have time, so, okay, I'll just move on. An nth-dimensional manifold, nth-dimensional, or a manifold for brevity, is a space that is, this is the hand wave definition. If you want to memorize something, this is very easy to memorize. The space that is everywhere locally diffeomorphic. It just defines what do you mean by diffeomorphism? Diffeomorphic to Rn. It's the same n, nth dimensional Rn. Okay. So let's have a very rigorous definition, very formal definition. So M is an nth dimensional manifold if number one, I'm just trying to interpret this mathematically. Everywhere. So everywhere so means for any point in M, right? Locally, so in a neighborhood around the point. So there exists a neighborhood of P in M, right? This is locally, I'm just interpreting. Everywhere for every point, locally, neighborhood around point, diffeomorphic. So there is a diffeomorphism. There exists a neighborhood P